So our next speaker is Rene Vidal from Johns Hopkins University. Thank you.
Hello, can you hear me? I started late, so I hope you don't count it against me. Thank you to the organizers for having me here, and happy birthday. It's been a great meeting, and I'm looking forward to the rest of it. So I didn't know when I came here that the people from Duke were not supposed to speak. And so I didn't know that the problem is that Guillermo is an author. So maybe that's why he stepped out of the room, so that he's not part of it. But he was not at Duke at the time this work was done, so I hope it still counts. I think several speakers have highlighted the fact that we live in an era of data deluge, where we have more and more data being acquired. And it's becoming increasingly difficult to be able to understand and process and do analysis of very high dimensional data sets. I work in the area of computer vision in particular, and just to give you a few statistics of how much data growth there's been over the past few years, there are on the order of 300 million pictures being uploaded just into Facebook every day, and about 72 hours of video being uploaded into YouTube every minute. Do you know how many pictures have been ever taken since the very first picture in the end of the 1800s? 3.5 trillion. And if we only had $1 for each one of them, we could probably pay a huge part of the US debt. Cisco estimates that 90% of the traffic by the end of this year will be videos. And the other scary part is that in the case of images, just 10% of this volume was just pictures taken last year. So we really need to start thinking about how to develop methods that are able to analyze large volumes of data. So in my own work, I'm not there yet, so let me just show you what that could imply even in smaller data sets, such as this simple video. This is one of the first movies ever recorded, and so there are these two guys that are trying to plot a robbery. And there is this lady that comes in, and once they get introduced, the guy starts flirting with the girl to distract her. When she's already distracted, the robbery starts to occur. Then the tiara goes to the other guy, and now he's late, he needs to go. So if I could take now a data set like this video and tell me, give me a summary of what happened here, what could I do? So how could I take all of the frames in this video and maybe produce a summary like this? If these were all the frames, and this is already a subset, the algorithm and the methods I'm going to be presenting today do precisely that. They extract a subset of all the frames of the video that, in a sense, I want them to be a good part of the story, that they're good representatives for the data. So more formally, this is the problem statement. I give you a collection of points, y1 through yn, and you would like to select a subset k much smaller than n in such a way that the subset that you select sort of efficiently represents the entire data set. I've given one example already on summarizing videos. You can also do this for text. Given, for example, all of the news of the day from CNN, can you extract a few highlights? The other possible application of this extraction of representatives is in classification. If I am given a very high dimensional data set with probably a large training set, maybe I can now take a very small portion of that training set and use those representatives in order to do classification. And of course, since I will assign data points to what the representatives are, that can also allow me to do some form of clustering of the data. So there's been a lot of work in trying to address this problem, but by and large, the methods can be classified in two big categories of methods. The first ones are those that try to model the data as living in some sort of subspace, and you try to select a subset of data points that capture the subspace. So for example, the rank revealing QR, you select a subset of the columns of the matrix so that the condition number is minimized. And then there's been a number of other methods based in general on matrix factorization techniques such as non-negative matrix factorization, randomized and greedy algorithms for selecting these columns that have been very successful. At the other end of the spectrum, you have methods based on clustering, because if the data does cluster in a number of groups, presumably you might want these exemplars to represent the clustering in the sense that you do get a certain number of exemplars for each one of the clusters of the data set. And naturally, variations of k-means, such as k-medoids, the big difference is that the cluster centers need to be data points, have been used. Methods based on set covering or affinity propagation have been very important to do that. But by and large, the challenges that remain is that the methods, these are all in general, selecting k columns out of n is an NP-hard problem. Many methods are based on iterative procedures that are trying to solve non-convex problems, so initialization is important. And many of these methods also, you need to specify what the dimensions are a priori, or what is the number of groups, and so on and so forth. So we would like to do, as much as possible, develop methods that are based on convex optimization that are, in general, more efficient. Ideally, we would like to be able to say something about the geometry, like what do the representatives that we extract for the data look like, and what is the relationship with the geometry of the data. And if possible, have some theoretical guarantees as to what the representatives do we extract, how do they correlate with the structure of the data. And so we have developed two techniques. The first one operates directly on the raw data and is based on the first family of methods that try to look for structural representations of the data, be it one subspace or being a union of subspaces. And the second one tries to look at nonlinear structure by not extracting the representatives out of the data itself, but rather out of similarities or dissimilarities between pairs of data points that can, as a consequence, be nonlinear. So let me start with the first method first. So again, this is the idea. I'm given a matrix. The columns of the matrix are the data points, and I have n of them. And I'd like to select a subset of k that represent the structure of the data. And I'm going to call those exemplars or representatives. So this is sort of analogous to classical PCA, where you try to factorize the data matrix into the product of a basis U and a set of coefficients C. Except that in PCA, that basis that maximizes the variance of the data need not coincide with data points. And as I said earlier, we would like this U matrix to be a subset of the data points. But inspired from the classical PCA, the key assumption we're going to make is that we would like the entire data set to be approximately represented as linear combinations of the exemplars that I'm going to try to select. And I have k of them. And this matrix of coefficients, which is little k by capital N, is what are the coefficients that allow me to express the data in terms of the representative. And notice that I have k different rows for this matrix here. But again, still, how do I select these columns? And given the selection of columns, finding the coefficients is easier. But how do I select the columns? So the way I'm going to do that is by expanding the dictionary, and instead of being just the exemplars, I'm going to take the entire data set as a potential dictionary. And correspondingly, I'm going to expand the number of rows of the C matrix that I have here. Now, obviously, I haven't done anything. It's still going to be the case that the data can be expressed as linear combinations of the entire data set. But again, I want to select only k of them. So what I'd like to do is to minimize the number of rows of the matrix C that are non-zero. And the number of non-zero rows is going to be exactly the number of exemplars that I'm going to select, k. And this problem of minimizing the number of rows of a matrix is, of course, non-convex and difficult to solve. So there's been a lot of literature on the fact that rather than minimizing the number of non-zero rows, you can minimize the sum of the norms of the rows. And here Q is something that you can choose, but obviously, typically, if people have chosen Q equals to 2, by and large, here we're going to be choosing any value of Q from 2 up to infinity. So, and then the way we're going to set up the problem is as follows. We're going to try to minimize the number of non-zero rows of the matrix, subject to the fact that the data is self-expressive namely that the data can be expressed as linear combinations of themselves. And we are also going to enforce that the coefficients add up to 1. And the reason for that is to allow for affine combinations of the data. But as you will see in the next slide, this actually has implications on the geometry of the representatives that gets extracted. And this is a well-studied optimization problem, and there are lots of tools to solve that efficiently today. So the main contribution really is, what does the solution to this problem look like in terms of finding representatives for the data? So the first result is the following. If you take the convex hull of the data and let K be the number of vertices in this convex hull, and you assume now that the data lies in a K-1 dimensional affine subspace, then the optimal solution of this optimization problem, assuming that Q is strictly bigger than 1, corresponds to actually the vertices of the convex hull of the data. So the representatives are just going to be the vertices of the convex hull, and rather than actually computing the convex hull and finding the vertices, you just solve this convex optimization problem that I've stated here. And this is what the optimal solution looks like. Modulo a permutation matrix gamma, you just get the columns of the identity matrix here. And so the non-zero rows correspond precisely to the representatives, and the delta matrix is strictly less than 1. The second theorem says, what if now the data is distributed not in just a single affine subspace, but in multiple affine subspaces? So in that particular case, the optimal solution of this optimization problem, again with Q bigger than 1, is such that you are going to select representatives from all of the subspaces. And moreover, the number of representatives per subspace is going to be at least the dimension of the subspace plus 1. So you are going to actually select sufficiently many representatives from the different groups that are present in the data, which is something that you would like. Right? So this is, again, the first method. This method operates directly on the data and is trying to look for subspace or multi-subspace type of structure in order to find the right set of representatives. What if now the data was sampled from a nonlinear manifold, and I wanted to also find a set of representatives for this slightly more complex setting? So what we're going to do here is that rather than operating directly on the data, we're going to operate on a dissimilarity matrix built from the data, where Dij, so D is going to be n by n, where n is the number of points, and Dij is effectively large if points I and j are very dissimilar, and it's going to be small if points I and j are very similar. And what do I mean by dissimilarity here? What I mean is that it's going to be small, Dij is small, if point I is going to be a good exemplar for point j. And so another interpretation is that Dij is the cost of encoding point j with exemplar I. How do you compute this dissimilarity? Well, you could use, it's application dependent, you could use the Euclidean distance or the geodesic distance, but for several objects, you don't necessarily need to have a metric. You can use whatever your favorite dissimilarity is for your very specific application. So how are we going to solve the problem? So let z, ij, be an indicator variable that is just going to tell me which exemplar gets selected by which point. All right? So Zij is 1 if y sub I is selected as an exemplar to encode point y sub j. So the cost of a particular selection of exemplars is precisely given by just this weighted sum of the dissimilarities Dij, because the Zij is either 1 or 0, and therefore I'm just going to add all of the dissimilarities of the points depending on what exemplars get selected. Right? So as before, I'd like to select very few representatives, and I can do that by looking at the rows of the matrix Z, and the number of non-zero rows is equal to the number of representatives. And as I said before, we're going to relax that norm by using the 1, Q norm, which is the sum of the norms of the rows, with Q being bigger than or equal to 1. And last, we're going to put the two objectives together. On the one hand, the objective of minimizing the cost of encoding all of the data points with the K representatives, as well as the fact that I like to select very few representatives. And that's going to be that we're going to minimize the sum of the two, where the number of representatives is weighted by a weight lambda. And the z variables, rather than being 0, 1, we're going to constrain them to be any real number between 0 and 1. And so that's why we require z to be non-negative and the sum to be equal to 1. And the sum to be equal to 1 means that every point needs to select one representative. Right? So, well, what are the properties of this optimization problem? What can be said in terms of the geometry of the representatives that are selected? So the first thing is that it depends on how you pick the lambda. If the lambda is too big, meaning that you penalize a lot selecting the K representatives, then only one exemplar will be chosen for the entire data set. And the exemplar that is chosen, in fact, can be computed, is the one that has the least dissimilarity with all the other data points, which makes a lot of sense, right? Conversely, if the lambda is chosen to be too small, then the optimal solution to this problem is the identity, meaning that every point selects itself as a representative. So in neither of these two extreme cases is a good solution, but this gives you a guidance on how to select lambda in between lambda min and lambda max so that you get representatives that are more meaningful. Now, the lambda min and lambda max are actually functions that can be computed from the dissimilarities directly, and if you're interested, here are the formulas, but it's essentially min max based on all the pairwise dissimilarities. So it's not an existence of some lambda. I'm actually telling you exactly how lambda min and lambda max need to be computed. The more interesting thing is now, let's suppose that the dissimilarities of the data are such that the data does cluster according to n different groups. So in that particular case, the theorem says that if you select the lambda to be small enough, then the optimal solution to the optimization problem will be guaranteed to select at least one exemplar from each one of the clusters. So again, the methodology is able to respect the cluster structure of the data by selecting sufficiently many exemplars, provided that you select the lambda to be sufficiently small. So here are a few experiments on synthetic data. The top row corresponds to q equals to 2, and the bottom row corresponds to q equals to infinity. And the different columns correspond to different selections of the lambda parameter. So in the first case, you're selecting lambda to be significantly smaller than the maximum. And this is just a two-dimensional data set, and these red circles means which points were selected as representatives. So what this is effectively showing is that you have data that you have two clusters, and you're selecting, in this particular case, roughly 6 points within each one of the clusters. As you increase the parameter to be now 0.1 or 0.9, the maximum possible, the algorithm selects just one representative per cluster. And when you actually make lambda be equal to the maximum possible, you only select one, which is what the theorem had predicted. So this is just an illustration of the theorem. This second example is on real data, and we're applying it to the classification problem. So we take the training set. In this particular case is the USPS data set of digits. And there are, in this particular case, 1,000 training examples per class. And out of those 1,000, we're only going to select 2.5% of them. And that's the selection of representatives. So the different rows correspond to different methods for selecting the representatives. The first row is what if you just at random select 2.5% of the total. This is the K-madoids, this is the rank-revealing QR, and the bottom one is the first method presented at CVPR. The different columns correspond to different classifiers. So the first one is a nearest neighbor, the second one is nearest subspace. This is the sparse representation classification proposed by YIMA, and the last one is SVMs. So the main point here is effectively that you are able to achieve with the more sophisticated classifiers effectively the same performance which is nearly 99%, with only 2.5% of the training set. Notice that in the case of nearest neighbors, however, you don't get such a good performance. And again, this is because the first method, the representatives are the vertices of the convex hull, and therefore something like k-medoids that selects cluster centers is in this particular case more appropriate. These are more examples on video summarization. This is a tennis game with Federer and Djokovic, and this is, again, you have the video and it selects a few frames that describes somehow the different events that are occurring in the video. Some are just very distant views with Federer either in the back or near the net. Some other ones are closer views and so on and so forth. These are some examples from a presidential debate between Hillary Clinton and Obama. And again, out of the entire debate, is able to select a few frames that correspond to the interviewer, then is Obama, then is some of the people attending the debate, and then when Obama and Hillary are together. So the key main distinct events are automatically selected by the methodology. And last but not least, this is probably going to be the first talk where the conclusions were actually automatically generated. So in this particular case, we took the NIPS paper, we took all the sentences from the NIPS paper, and each such sentence becomes a data point. We computed, using techniques that you can find in the details in the paper, a similarity between two sentences, effectively a type of bag of words type of similarity. And then we took all of the sentences of the papers and now selected the top 4 representatives. And here are the representatives of the NIPS paper. So given pairwise similarities between data points, we consider the problem of finding a subset of the data called representatives or exemplars that efficiently represent the data collection. We obtain the range of the regularization parameter for which the solution of the proposed optimization program changes from selecting 1 representative to selecting 1 representative per class. When there is a clustering of the data points, it works, and I guess you can read, right? Thank you so much for your attention. And by the way, Guillermo is an author, so he's happy to take the questions.
I think you put a lot of pressure in the last speaker because the 3 speakers were outstanding talks and outstanding on time. So the last speaker has a lot of pressure, not if I need to add pressure on you, but anyway, we have Mauro. Go ahead. Yes, Guillermo. So, no. I'm just the observer here. So seems that I think before you get repetitive repetitions, then there is also a smaller problem about the generation. So if you're representing Sparse and so on, that doesn't necessarily mean that you can generate new samples or new instances of your data. On the other hand, modeling data might involve eventually being able to generate data. Are you thinking about so do you think your work can be through generative models for data, or not, or what are the?
So the first answer is that we have not thought about it, so I'm just responding in real time. The first method, if you remember, is effectively almost like the data points are linear combinations of the dictionary with some regularizer on the coefficient. So that's naturally a generative method. Whether that works in all of the applications that I mentioned about is something that we have not explored. For the second method, it's a little bit more difficult, and I don't have an answer. And the question is, I have similarities, I generate the representatives, and now these are trying to capture some nonlinear manifold. How could I now generate samples? Again, I think if the similarity is something based on a Euclidean distance, presumably the first method would be applicable. But more generally, I wouldn't know how to go about it.
Any other? That side of the room has been very quiet for the last hour and a half. So maybe I'm not looking. I just want to make sure that I look in that direction if there are questions. This side has been overrepresented, so following the, no, I want to make sure I'm not biased to be on this side. So, yeah, I give enough time, so. You mentioned that you find the range of regularization parameters for which you have to exclude things. I was wondering if you have any method for finding the approximation for the optimal case, if optimal will be selecting one example per cluster. You mentioned that you have if the lambda is sufficiently small, then you have this very sparse representation.
Yes. So when lambda is equal to lambda mean, only one exemplar is selected. And right before that, you effectively select one per cluster. We don't have very precise analytic expressions as to when that happened, but the paper does have a lot of numerical examples precisely showing what is the number of examples per class that are selected as a function of the regularization parameter. Being able to guarantee exactly that you get one per class, I don't know if it is entirely trivial. If you saw, in one case it was 0.9 the lambda max, in the other case it was 0.1 the lambda max, depending on what the value of Q was. So we don't have an analytic expression, but I believe that if you just select an epsilon smaller than the max, then you will get one per class. Sorry, I couldn't hear the beginning. Yes? Yes, it depends on lambda, of course. Yes, all of the you have the plots in the paper, and it depends monotonically on lambda. No, we don't have a proof, but I believe it is so, or I conjecture.